So today what I want to talk about is some latest insight about how we know about the evolution of planet-forming disks. One of the most fundamental questions in astrophysics is to understand how planets form and what conditions we can form habitable worlds. So we can study exoplanets. We can also study solar system planets. We have many informations. And the third place we can get insight about how planets form is to look at the places where planets are forming. So it's moving. Okay, yeah. So planetary system, we know they are the natural byproduct of star formation. So planetary forming disks can start to form around young stars because angular momentum need to be conserved. So you will have those accretion disks around the young stars, and those are the birthplace for future planetary system. Those gas-rich disks, they can last for a few million years. After a few million years, the gas disk is gone, and hopefully by then you would have some gas giants in the system. So we want to know those protoplanetary disks, how they evolve, how the conditions will nurture the planetary system, how they define the characteristics of future planets. In particular, one of the most fundamental property of protoplanetary disk is their mass. Because those masses, we think initially 99% of them is in molecular hydrogen and helium. So the gas phase materials takes 99% of the mass initially, only 1% of the mass is in the solid phase. So since gas is the dominant component, it plays an essential role in almost every step of planet formation. So from the beginning, the gas interaction with dust particles, they regulate the dust oscillations, how they grow to larger particles, to kilometer-sized planetesimals, eventually to planetary cores. So we want to know the amount of gas in the system, how they regulate those solid body growth. Also later, the amount of gas available in the disk directly determines what type of planets we can have, whether we have enough mass to form a gas giant like Jupiter, or you ended up more like ice giants like Neptune, or you don't have much gas when the planets form, so you may end up with super Earths. And finally, after planets formed, so they may migrate across the disk. So how they migrate, in what speed, in what direction, also depends on the gas distribution in the disk. So in the end, it is every fundamental step of planet formation, we want to know how the gas is distributed across the disk and to get our knowledge about how planets form. So there are two fundamental theories about the gas distribution in disks and how they evolve over time. So the key thing is trying to understand how the angular momentum is transported or removed from the system. So there are two ideas in general. One is a classic idea. It's very old. So the idea is the gas viscosity is mainly dominated by turbulence. And in this case, most of the disk mass lose their angular momentum. Those materials will falling in accreted towards the center star. And a small amount of the gas getting angular momentum and they spread out. So they carry angular momentum outwards and most of the materials can fall in. Another idea is instead of redistribute the angular momentum, instead you can remove angular momentum from the system directly. So this is done, you have materials near the disk surface and those materials maybe get accelerated along the magnetic field line. So once they have enough speed, they can leave the disk and remove those angular momentums. In both the cases, you want to remove angular momentum from most of the materials, and those materials can be accreted towards the central star. But we still don't know how exactly those mechanisms work and which mechanism may play of most dominant roles. There has been two approaches trying to determine the roles of each mechanism. So one idea is you can look at individual disks to look at the predicted signature of different mechanisms. For example, you can look at turbulence levels, but this is very hard to measure. Most of the turbulence measurement effort turned out to be non-detections, and only a couple of disks we have some constraints. Similar situation is also in the disk wind tracer. People have tried very hard to find signatures of disk wind. Although there are detection of disk wind, but connecting back to the disk involution mechanism has also been difficult. So another approach to look at this is instead of looking at characteristics of individual disk, we can also look at the disk properties, how disk as a population, their general properties, like their mass, their disk sizes, their accretion rate into the central star, how those properties change over time for disk as a population. So this is sort of like an HR diagram for stellar involution. You can also look at those properties instead of the effective temperature luminosity. You want to look at the mass, the size, how those properties changes. But with this approach, you need to have a well-characterized population in order to do a population study. And this has only been done for the dust mass, so solid mass in the disk. And I should say dust mass because that's the observable part. So, but as we said before, we know most of the disk mass should be in the gas phase. So the fundamental involution should be dominated by the dominant mass component. We want to study gas directly rather than rely on some proxy. Also, so we know disk evolve over time. One of the most fundamental involution signature is we find the protoplanetary disk based on the infrared axis compared to the stellar photosphere. So this is, we can look at nearby star forming regions to look at young stars, which shows those infrared axis features. And so this is one of the classic pictures. When you look at different star forming regions, you find the fraction of young stars with infrared axis. So implying they still have a dusty, gas-rich disk around them. So their fraction decrease over time. So that's the typical referred to the lifetime of protoplanetary disk for a few million years, mainly from the fraction of disks, young stars with infrared axis. So we know the disk population evolve over time. And over the past decade, there are also enough data from the dust study. We also know the dust mass of protoplanetary disk. They seems also decrease over time. So particularly you see those around 1 million year disk across different star forming regions, they seems to have similar median dust mass, but really you see a big jump when you go into the older population, a few million year old population, they have much less dust mass. So we know those disks, they evolve, but we still don't know how their dominant mass, the gas component, evolve. So based on some simple predictions, we could say if we can measure the gas disk mass and the gas disk size, how those properties change over time, we can potentially distinguish the two leading mechanisms. So for example, the viscous example predicts the disk will increase over time, while for the wind evolutions, the observable disk size should shrink over time. So this is a simple analytic prediction, but this is giving you the ideas. If we can measure the gas mass and the sizes over a large population at different ages, we could tell which one is the dominant mechanism. So that's what we're trying to do with the age program. So this is called the ALMA survey of gas evolution in protoplanetary disks. So our goal is to systematically trace the evolution of gas disk mass and the size across the lifetime of protoplanetary disks. So this is the first systematic program trying to collect a significant sample of disk mass and size information across different ages and compare with evolution mechanisms. So this is our team. It's really international. And all the work I present today is a huge effort from the whole team, and particularly from the postdocs and the graduate students who really did the heavy lifting work here. So all of the data have been taken, and we have all the papers written up now. So those are in the revision stage, and hopefully will coming out in the month or two. So the basic idea of this program is to choose a sample which covers different ages and trying to study this mass and size evolution. So the design is we have total 30 disks crossed from roughly 0.1 to a few million years. And those disks are chosen from 3 star-forming regions because the individual age of disks are very hard to determine accurately for those young stars. So instead of relying on individual age measurement, so we choose typical star-forming regions. They represent different ages, so to increase the accuracy. So we choose Ophiuchus, so that's generally considered one of the youngest star-forming regions nearby. So in particular, we choose the class 1 disk. So you can think about this is the sample represents the less than 1 million year population. And we have an intermediate age sample from the lupus star-forming region. So that's generally considering 1 to 3 million year old. And the oldest sample from the upper school region, so 2 to 6 million years. And so since our focus is trying to focus on the evolution effect, and that could be stellar mass dependent. So we try to narrow the stellar mass range. So focus on M3 to K6, roughly 0.3 to 0.8 solar mass stars. And we're trying to focus on single stars or wide separation stars because the close binaries, they have tidal interaction may change the disk evolution patterns. So the idea is we choose 10 disks from each region. And so you can see this button showing you the millimeter continuous flux from our sample. So you have the youngest region, so the millimeter flux is the highest, so indicating they have more dust mass. And in the intermediate age, you can see also this is between 1 and 10 millijansky, so they have in the intermediate amount of dust mass. And the oldest disk sample, they have the least amount of dust mass. And those changing of disk mass, this dust disk mass is already known in this many studies of disk dust evolution. So the key part of our challenge is how we can accurately measure the disk gas mass. So traditionally in interstellar medium, when we talk about measuring gas mass, people usually use the carbon monoxide because the carbon monoxide has a conversion factor with H2. So the number density factor of 10 to minus 4, you can measure carbon monoxide and convert that to H2 mass. So naively, we would think this would be the similar situation for protoplanetary disk. We can do the conversion by observe CO easily. Sorry, I forgot to explain why it's very hard to observe H2 directly, because H2 is a symmetric molecule. It doesn't have a permanent dipole moment. So it does not have strong radiation lines at the cold temperature range where the bulk of the mass of the protoplanetary disk. So we have to use another molecular tracers. And CO is the most widely used one. But for protoplanetary disk, recent study has shown the CO to H2 conversion factor has a large uncertainty. So this is showing you for the youngest regions less than 1 million years, so the CO to H2 ratio is probably still interstellar medium level 10 to minus 4. But when you move to 1 million year or older disk, there is a pretty wide range of possible CO to H2 abundance ratio. So particularly, you can see those regions, we have 2 orders of magnitude uncertainties. So if you just measure CO, what you turned out, your gas mass estimation, you will also have 2 orders of magnitude uncertainty. So the question is, how can we improve this accuracy? So here we added additional chemical tracers. So the choosing tracer is N2H plus. So this is because the N2H plus chemistry is known to depend on the CO gas phase abundance. So N2H plus is easily destroyed if gas CO is around, so you can form HCO plus. At the same time, the formation of N2H plus, it's a competing process with CO. So N2 needs to combine with H3 plus to form N2H plus. At the same time, CO is also reacting with H3 plus to form HCO plus. So because of the 2 competing process and the destruction pathway, N2H plus is only abundant in the CO poor gas. So as a result, we can use the N2H plus to CO isotope log ratios. So you measure the flux ratio of the 2 molecular line emissions. That's an indicator of the CO to H2 abundance ratio. So when you have a CO poor gas, you will have more N2H plus. When you have CO abundant gas, you will have low N2H plus to CO ratio. Okay, so this we have done a benchmark test with 3 disks, and the only 3 there are an independent measurement of gas mass, which is from the deuterium and hydrogen. And those measurements were done from the Herschel Space Telescope. Because Herschel, we don't have far infrared space telescope now, so that's the only 3 fundamental data points we have. We can do the benchmark test. Okay, so this is showing you the gas disk mass. So those colored dots is if you just take the CO line flux measurement, converted to gas mass, because of the CO to H2 ratio has 2 orders of magnitude uncertainty, you will have 2 orders of magnitude uncertainty in your gas mass. So those colored dots showing you the possible range of the gas mass for each of the 3 disks. But if we add the information about N2H plus to CO line flux ratio, then you have the orange box region. You can say it dramatically shrinks the possible parameter space by a factor of 5 to 10. So that's what we can get with the combined method. And you compare the orange box with the gray box, which is the inferred gas mass from HD measurement. So you can see they're generally consistent with HD measurement. Okay, so this method basically paved a way to measure gas disk mass in a large population of disks. So that's the method that we use. So the key science lines are the 12 CO, the most abundant CO1, which we use to measure the gas disk size, and the 2 CO isotope logs, 13 CO and C18O, which have different optical depths to help us constrain the CO gas mass. And finally, we have the N2H plus line, which used to calibrate the CO to H2 abundance. So those key science lines are what we use to measure the gas mass and the size. And we also have a bunch of other molecular lines, which serendipitous observations. So this is showing you the continued emission from the 30 disks. Our resolution is about 0.3 to 0.4 arcseconds. So it's not a very high resolution, on the order of 40 AU. So some of the disks are pretty compact, so they look like point source. And on the right is the 12 CO line, integrated line emission image. So for the youngest sample of UCAS region, you can see they look very asymmetric. That's because 12 CO have cloud contamination, so the envelope residual materials may contribute to it. So which makes it harder to measure the gas disk size for those youngest sample. But the other disk in the lupus and the upper score regions, the middle age and the oldest sample, they look regular, and we could measure the gas disk size from the sample. So from the first group of H4 results, we have 12 papers. Those are all submitted. Half of them are accepted now, and half of them are still in revision. So we have an overview paper explaining the design of the program and have some highlights of the main results. And we have 3 papers describe the observations at each star forming region and the general statistics. And then we have 3 papers describes the method, how we use the results to measure the gas mass, the dust disk substructure, and the gas disk sizes. And we have 3 theory papers to compare theoretical prediction with our observations, including comparison with the dust simulations with our observations. And the second paper, we do population synthesized models to compare MHD disk wind and the viscous evolution disk plus photoevaporation, how those compare with our observation of the mass and the size. And we also have a paper to evaluate the impact of external photoevaporation. And so the last, we have 2 papers. We call them beautiful surprise because we didn't expect them. One is, there is an interesting disk which have some hint of so-called planetary disk. And the other disk, which seems to be variable at the millimeter continuum flux, which is pretty rare for protoplanetary disk. Okay. So I wanted to then dive a little deeper into our results for the gas disk mass. So as we mentioned, we use the CO isotope logs and N2H plus. Basically, those are the key lines to measure the gas mass. So our method is, it's too expensive to run individual disk matched models. Our approach is to run a large grid of thermochemical models, including the basic gas chemistry and the simple green surface chemistry to calculate the gas temperature and estimate the line fluxes at different disk properties. So including changing the disk mass, gas to dust mass ratio, CO abundance. So my postdoc Leon Chapman, he really did most of the work here. So once we have the large model grid and we compare the model predicted line fluxes with observations and trying to calculate the posterior distribution for different parameters, in particularly the gas disk mass and the CO abundance. So you can see this is the posterior constraint for particular disk after we compare our model grid with the observations. So this is a plot showing in our 30 disks how the dust disk mass compare with the gas disk mass. So this is the minimum solar nebular mass, so about 10 to minus 2 solar mass. And this is Jupiter mass, about 10 to minus 3 solar mass. So the colors, the gray colors is the youngest sample, and the orange one is the intermediate age, and the teal color is the oldest disk. To find across different, even within a star forming region, there is a wide spread of gas disk mass. But you do see some difference in the medium gas disk mass. So particularly the youngest disk, so the Ophiuchus disk sample, their medium gas disk mass is on the order of slightly less than the minimum solar nebula. So it's around 10 Jupiter mass-ish. And you find this median gas disk mass drops by nearly order of magnitude when we come to this intermediate age. So this becomes less than 1 Jupiter mass, about 0.8 Jupiter mass. So surprisingly, when you go to the latest, the oldest sample, the mass does not change that much. So it drops a little bit, only 15% compared to the intermediate age. So this was one of the biggest surprises in our sample is we were expecting to see dramatic gas mass decrease like the dust mass. But we are seeing the gas mass seems to decrease very quickly at the beginning, and then it flattens out. So this was surprise, and we say, is there something related to how we do the model? But we went back to look at the line flux, which were directly measured from observations. And so this is a continual flux versus a different CO line. What we are seeing here, the two groups, so the orange group and the teal group, except for this outlier, you can see on the y-axis, the line flux range, they covers a very similar parameter space. So this is the same thing when you look at the N2H plus. So you find the orange group and the teal group, they seems to be pretty similar in the line fluxes. So no matter what model you use, trying to get the gas mass of the two groups, you will find that they would have similar gas mass because the line properties, the line flux seems to be very similar distribution. Okay, so we confirm this is not how we interpolate the line flux to gas mass. So whatever model you use, you will find the two population, even they have quite different ages, quite different dust mass, their gas property seems to be similar. Okay, so if you plot these three regions, trying to look at their dust mass, this is how they would look like. So each region, we know they have a big spread, but the median value seems decrease over time in terms of their dust disk mass. When you look at the gas disk mass, you see a different picture. So the gas mass decreased quickly over the first 1 million years, and then it slows down. So it's not like the dust disk mass seems to be steadily decreased, while the gas evolves on their own time scale. So this leads to an interesting swing in the gas to dust mass ratio. So the youngest sample we have, their gas to dust mass ratio is around 100, which is expected, the interstellar median value. And when you go to the intermediate age group, you'll find the gas to dust ratio becomes smaller on the order of 30. This is because even both the dust and the gas decrease much faster at this first 1 million year. And then when you go to the latest, the oldest group, you find the gas to dust mass ratio comes back. That's because this stage, the gas is not changing that much while your dust mass is still decreasing. So you have this interesting change of the gas to dust ratio, first decrease, then increase. So this has some fundamental implication about the planet formation conditions. I think this is different from the traditional view. You either have a gas to dust mass ratio decreasing over time, or in the dust population models, usually people find due to the dust draft, the gas to dust ratio increase over time. But we are seeing a changing pattern, first decrease and then increase again. Okay. So from those observations, we also measure the gas disk sizes. For embedded disk, we could measure where their rotational pattern changes from Keplerian to in-4 patterns. So this is a work in progress. And for the class 2 disks, they don't have cloud contamination, so you can directly measure their 90% of the flux where it's from. So that's usually used as a characteristic radius for the gas disk size. So this is a distribution of how extended the gas disk compared to the dust disk. So most of the disk seems to have a 2-to-1 ratio when you compare it to the gas disk size to the dust disk size. Important things, most of the disk looks pretty small. So medium disk size is on the order of 70 to 100 AU size. Those are factor of few smaller than other very well studied gas disks. So that's a suggesting the general population of those protoplanetary disks, the gas disk is rather small, not the well-studied ones people find a few hundred AU or 1,000 AU sizes. Okay, so we have the disk properties from this survey putting together. So you have seen this, the dust disk size, the dust disk mass, and gas disk mass, gas to dust ratio. And we also measure the dust disk size. So across the 3 regions, this seems to be pretty similar. So on the order of 30 AU. And the gas disk size is between 70 to 100 AU. So you'll find the 2 regions, the Ophiuchus, the lupus and the upper skull are pretty similar. We don't have Ophiuchus size here yet because of the cloud contamination, made it hard to measure this. And finally, also with the NH plus to CU flux, we could measure the CU abundance. And you find the 2 regions are pretty similar. And they both seem to be depleted in CU compared to the interstellar median value. And finally, we have the spectral index, which is the continual flux, how it changes with wavelengths, are often used as an indicator of the maximum dust size in those disks. So you see upper score have a significantly larger median spectral index compared to lupus. So that's an indicator of the bulk part of the upper skull, the dust particle we are seeing seems to be in smaller size compared to lupus. Okay, so that's the observational properties we measure from the program. And we're trying to put this into a context of different disk involution mechanisms. Okay, so first is the dust involution. Our collaborator, Niko Katovic, is a postdoc at MPIE. So he did a dust particle involution under viscous disk involution models. So he ran a comprehensive dust grid, starting with different initial conditions, different viscosities, and different pressure types. So you can think about mimicking a Jupiter planet or a Neptune mass planet in the disk, which can open gaps and traps dust particles at different locations. So this is a simulation with relatively strong dust trap at a few radial locations. And then he turned those simulations into simulated observations and to say what's the dust disk size and what's the total continual flux at our observed wavelengths. And then he can take these properties to compare with our AgePro survey. So he had basically three types of models. I know this plot is busy, but focus on the bottom first. So this one is showing for different stellar mass and different ages. So from this 0.5 million year, 1 million year, 5 million year, 10 million year, how the measured millimeter flux for the continual emission will change over time. So if there's no pressure type in the disk, the dust particles, they will grow and drift towards the central star. So gradually you lose dust, and you can see the continual flux decreases over time. So that is a prediction, and this decreasing. And those stars is our observations, where the stars lies compared to the simulations. So in particular, you can say for the older samples, so for the intermediate age and older samples, the quickly, if no pressure type inside, so our observations are slightly larger compared to the simulations. So towards the upper end or above the simulations. And in the middle column, he simulated in a case if you have Neptune mass planets in the system, so which produce intermediate level of pressure type, which can keep some dust particles in the system. And this is how the observed line continual flux compared to his simulations. So you can see it's a better match with the spread of the models. And finally, he also generated if those disks have very strong pressure trap, which allows very little amount of dust to drift inwards, how the flux will change over time. And you can see this is also roughly consistent with observation, but have less good match compared to the weak pressure type one. So he also checked how the spectral index, so which is the dust particle size indicator, would change compared to our observations. So same idea, no pressure type at all, weak pressure type and strong pressure type. And you can see in this case, the weak pressure type 1, which is very poor case to reproduce the observations. And so the weak and the strong pressure types do better. In general, when he considering all the observable parameters, he concluded a weak pressure trap seems to does the best match with our current observations. Okay. So of course, we wanted to do our gas evolution and to test the viscous evolution and the MHD disk wind evolution. So this one, we tried the population synthesized models. So this was mainly carried by Benoit Taubon. So what our approach is, we take our observables and do a random start of initial conditions and then let the population evolve. And we check, compare with our observations, what are the parameter space allowed in order to reproduce observations. Okay. So the four type of the observable we have is, we know at different ages, what fraction of disk we know, what fraction of young stars we know they have a disk. And we know the accretion rate of those disks to their center star. So this is, you can measure from accretion tracers or from UV access. So those are from literatures. And the new observation from the H-Pro itself is, we now know the gas disk size in the sample, and we know the gas disk mass in the sample. So you can see the spread here and the median value from our observations. So we try to find in a semi-analytic prescription of those disk evolution mechanisms, what parameter space we could reproduce these. So basically, he find in his best fitting models, so MHD disk wind can roughly matches with those observable properties. He was able to find a parameter space, which generally start with relatively compact disk and a weak magnetic field. He could reproduce those general properties. But for viscous evolution disk, it has been very challenging to find a consistent solution to match all the observed properties. In particular, it's very hard to match the disk fraction and with the accretion rate, gas disk size. And in those three, when you satisfy those three things, you find that your disk mass is over-projected for the intermediate and old age. So this is his best model you find with the lupus sample and the upper school sample. So the gas disk mass over-projected compared with observations. If you're interested in individual disks, there is how the two mechanisms predicted the probability compared with our observations. So compare the gas disk mass with accretion rate. So this is the distribution, the red dots is our data. And the different color in blue indicate the probability you can reproduce those. And you find in the MHD disk wind model, so you can have 90% of the chance you can have simulations within the observed property space. Well, with the turbulence case, it's harder to reproduce the parameter space we observed. Okay, so that's for the ALMA part. I wanted to just briefly show you our latest JWST observations. So we have JWST follow-up for the same sample of 30 disks to observe the inner disk composition. So you can observe water and different type of organics to see how the inner disk composition would change over time compared to the global disk property evolution. So all the data have been taken, and this example from the 3 regions. So again, green color is the youngest one, orange is the intermediate, and the teal is the oldest one. So you can see those absorption features from ices in the younger disks. And what we are seeing, it's very interesting. There is notable difference in the chemistry across different regions. So for example, this is showing you waterline luminosity. So from representative lines, so this is a line with upper energy temperature 6,000 Kelvin. So you can think about represent a hot component, about 1,000 Kelvin water. And the y-axis is a cold water component. It's about upper energy 1,500 Kelvin. So hot and cold water. So the green color is our youngest sample, and the orange color is the intermediate sample, and the teal is oldest sample. So you can see there seems to be a systematic shift about the water luminosity across the different samples. We seem to be moving from the very water-rich cases and towards into fainter and fainter water emission when you go to the older regions. So this is also seen in the number of species we see. So the youngest regions, we mostly detect water and some simple organics. When you're moving to the oldest disk sample, it seems you have more organics detected in the spectrum. So you can see you highlighted some very carbon-rich ones here. So even with some isotope locks. So this is at still a very earlier stage, but from the spectrum itself, we are seeing significant changes with ages. So this suggesting the inner disk chemistry seems to have some significant evolution over time. And one particular prediction from the framework of pebble drift, so this seems to suggest a consistent picture from the very earlier view. So this is showing how the pebble flux, the black line as a pebble flux, will change over time. So basically current dust involution model, if no pressure trap present in the disk, you have very high pebble flux drift inwards at the earlier 1 million year, and the flux decrease over time. And if you think those pebbles are pebbles with ice on top of them, when those ice are carried into the inner 1AU, they will sublimate, bring water to the inner disk region. And so the amount of water they bring will decrease over time, right? So this seems to be consistent with what we are saying. The early disk seems to be pretty water rich, and the older disk seem to be have less water. And also another thing is when you compare the amount of water to other carbon carriers, so there seems to be a continuous shift of the C/O elementary ratio in the gas, how it changes over time. So this very earlier stage is very hard to observe, but we can start to see things from 0.1 and later million year. So basically focus on this increasing trend here. So this is suggesting current pebble drift model predict the C/O ratio in the gas in the inner 1AU region would increase over time, which is consistent with the picture we are seeing. We are seeing increasing organic species in the older disks. Okay, so very preliminary, but I'm pretty excited by the difference we are seeing in the JWST spectrum. Okay, so the take-home message is the H-Pro is the first systematic survey trying to trace the gas evolution in disks. And we find the gas and dust, they seems to evolve at different time scales. And compare the MHD disk wind and viscous disk. Based on our observational properties, MHD disk wind model seems to have does a better job in reproducing those observational properties. Yeah, and so hopefully I will show you. We have some more picture about what the JWST part tells us, our inner disk chemistry. Yeah, thanks.
Any questions to Coco?
Thank you for the wonderful talk and the results. So just focusing on this figure, so on the dust mass evolution. So it's the wonder, how do you measure the dust mass? Since I believe many of them, especially young system, it's quite optically thick. You could underestimate the dust mass. So if you take that into account, will it change the trend? So if you go to younger system, you underestimate more, so you naturally have slopes.
Yeah, that's a very good point, because for the younger systems, we used the same dust temperature and dust opacity to calculate the dust mass with the assumption of optically thin emission. So for particularly youngest disk, they have the most massive cases. So we could be underestimate those dust mass. So we actually have a follow-up program to get multi-wavelength observation for the same 30 disks. So all the data have been taken, but there is a graduate student in my collaborators group, and he is working on to do multi-wavelength analysis, which would have a better constraint about the dust size distribution, the opacity, and the true dust mass. Yeah.
So, quick question. So, for the GMST, people also find that in lower mass there are more carbon-bearing molecules. And is the reason the same as this age, because the evolution is faster for lower mass?
Yeah, it could be. So there has been a trend to find a very carbon-rich species in those very low stellar mass disks, like say 0.2 solar mass or 0.1 solar mass disk. They seem to have very organic rich. So we don't know which one, whether the stellar mass or the evolution, which one drives the main difference. But could be, as you said, because the low mass, the disk, they could be involved faster, and then the inner disk becomes more carbon rich at the earlier stage. Yeah, so I think we need more sample to know that. Yeah, so for our sample, we are slightly more massive. So we are at the 0.3 to 0.8 solar mass compared to the known very organic rich ones. They are usually around 0.1 to 0.2 solar mass.
Hey, I'm curious, like, so what's the plan on like connecting the outer disk observation of ALMA on the GWC very much inner disk? You measure, probably both measure CO from the outer disk and the inner disk, or from the preliminary estimate evaluation, are those two in general consistent with each other? Like when you look at the mass of population.
Yeah, so for the inner disk, although the JWST spectra give us CO spectra, but those CO are very optically thick. So we're only tracing the surface layer. It's very hard to convert back to the disk mass. Yeah, but we are mainly interested how, if there are any correlations about the disk chemistry evolution compared with the global properties. Yeah, and also substructures in those disks.
I was wondering about the dust radius estimates or observations. So if you do like a normal dust evolution simulations without any pressure bumps, then typically the dust size of a disk will decrease with time. However, of course, if you do have a pressure bump, then that's going to maintain the disk. So could the reason that you like don't see a big change in time just be that you simply see the big disks that all have rings?
Yeah, so that's an excellent point. So actually the picture we are promoting is those disks, they have some pressure trap, but this cannot be the strongest pressure trap because we do see the dust mass decrease over time. But also we see the dust disk size, the 90% of the flux radius seems to be rather consistent. So you can reproduce this with the weak pressure trap case. You still trap some dust in the outer disk regions with a weak trap, but still it allows some fraction of the dust mass to drift inwards. So that's the picture we think are most consistent with what we are seeing here.
Just to follow up on that, if the big trap is the case, then it basically requires a Neptune to form pretty far away in 1AU.
Yeah, so this is saying if you have like say Neptune planets around 30 AU, so that can keep the dust particle at, yeah, but you don't need to be very further away because these are like 30 AU size. Yeah.
Yeah, I also have a similar question. So I just wonder if it is useful to like plot the real fraction of the real dust mass distribution or gas mass distribution, considering like say only 10% of it exists at the very late stage. So what you are comparing now is actually given that the disk still exists, what's the mass distribution, what's the dust size distribution? Is it useful to say like given a star is formed, like what's the final like at that stage, what the like, average or the distribution of these quantities are?
Yeah, certainly. So that's taking into consideration in the population synthesized models, because that considering the disk fraction. So it first matches the disk fraction at different ages and then try to reproduce the median value of the observable properties. Because we are choosing, this is a particular problem for the upper score regions because we are choosing disk from the survivors, right? If there are only 10% of the star has disks, so what we're saying the property here is the median property of the 10% of the disk. But that in the population comparisons, we're taking that into consideration.